All right, so this was the problem that was assigned. And it's a polar coordinates thing. It says, okay, so R is sine of t, and theta is cosine of 5t. And so let's see. First, we want to calculate the velocity. Man, I don't have, well, I have it from before. I would have to derive this again to. Okay, so. All right. I had to cheat for a second. Okay, so what's the velocity of this thing as a function of time? So the velocity is r dot, r theta dot. And so that is, well, let's calculate these things. Okay, so r dot is cosine of t. R double dot is negative sine of t. Theta dot is negative 5 sine 5t. Theta double dot is negative 25 cosine of 5t. And so the velocity vector is cosine of t, sine of t times negative 5 sine of 5t. Maybe simplify that a little. Okay. So the first couple of questions are really just plugging this into formulas. The acceleration as a function of time. So the acceleration is r double dot minus r theta dot squared. And then for the second component, r theta double dot plus 2r dot theta dot. So that's negative sine of t minus sine of t times negative 5 sine of 5t squared. And then for the theta component, the second component, sine of t times negative 25 cosine of 5t plus 2 times cosine of t times negative 5 sine of 5t. And you can simplify that, but I'm out of room, so that's all I'm doing. Okay, so for what value of t does the polar coordinate system first align with the standard coordinate system? Okay, so when does our our theta coordinate system first align with the xy coordinate system? Well, what would it take for those two to align? It would take the r axis to be horizontal, to match the x-axis, right? And so that would mean that theta has to be equal to 0, okay? Or 2 pi or 4 pi or whatever. That means that, cosine of 5t has to be equal to 0. So that means that 5t has to be equal to pi over 2. And so the time is pi over 10. Somewhere around 0.3 seconds or something like that. Okay, are you with me on that? At the time that we determined just now, what is the velocity vector expressed in the standard coordinate system? Okay, so if we plug it into this formula, if we plug t equals pi over 10 into the formula we just got for velocity, we'll come up with the velocity vector in the r theta coordinate system. But we just figured out that that's exactly the same orientation as the xy coordinate system. And so in this case, we don't have to do any changing. We can just plug in pi over 10 into our formula, and that, because they're aligned, gives you the xy components. Are you with me on that? Or is that a little hazy? So the velocity vector in the r theta, let me write it like this, is cosine of pi over 10 negative 5 times the sine of pi over 10 times the sine of 5 times pi over 10. So that's pi over 2. And, we could approximate this. No. So that is 1 for the r component, the first component. I thought you thought that answer was really funny for some. Pi over 10 times sine of pi over 2. And that's basically 0. Okay. But at that instant, those two coordinate systems align, And so this is also the velocity vector in the XY coordinate system. Okay? That was part D. What's the acceleration vector? I'm going to skip that, but it's the same, like plug the time that you calculated into your function. That gives you your r theta velocity vector. And then the next step, no matter what r theta is to re-express that in the XY coordinate system. Okay. In this case, since those two are aligned, you don't have to do any conversions. But then the last thing is it's asking for what's going on at t equals 0. Okay, so I'm going to just do the velocity again. So E, that's just the acceleration. But F, we want to calculate the velocity at time equals 0. Here's our velocity function. So our velocity vector in the r theta coordinate system is cosine of 0 for the r component, and then a bunch of sine stuff, so 0 for the theta component. Okay, but theta, but the r theta coordinate system doesn't align with the XY coordinate system at this instant. Okay, because remember the r theta coordinate system always has the r axis pointing straight at the particle. Okay, so let's see what theta is, and that'll tell us what the, so theta is equal to 1. So, and that's equal to somewhere around 60 degrees. So, so 57.3 degrees. Okay, so this is the r axis, and this is the theta axis. And we want to express this velocity vector in that red coordinate system. You could do it as a series of like projections, dot products. The easiest way to do it is to use a rotation matrix. So that's what I'm going to do here. So if we wanted to go from, if we're going from a coordinate system like this to a coordinate system like this, what rotation would that be? Yep.
That would be a rotation about the z-axis.
The z-axis, that's right. And it's going to be a magnitude of 57.3 degrees. Is it going to be a positive or negative rotation about z?
Negative.
Negative, that's right. It's clockwise. So theta is equal to negative 57.3 degrees about the z-axis. Okay? So the rotation matrix is cosine of negative 57.3 sine of negative 57.30, negative sine of negative 57.3, bless you, cosine of negative 57.3, 0, 0, 0, 1. Okay, so let's calculate this. This is fast if you have it programmed into your calculator. It's sort of tedious if you have to do what I'm doing, just type this in. Still not too bad. And we're multiplying this by the velocity vector in the r theta coordinate system. So the velocity in the xy coordinate system is q multiplied by what we got before. That was 1, 0, right? 1, 0, you got to give it the z component too. And so you get 0.54, 0.84. And you get a 0 too, which you can ignore or put in. Okay. Any questions about that? So what you're doing in this problem is, I mean, you're just plugging values into a formula, into formulas that I got before that you have in your notes. But then once you do that, you have to consider the fact that at every instant, if you want to express it in the end in a horizontal, vertical, XY coordinate system, you have to deal with the fact that instant by instant, those coordinate systems are in different orientations, okay? And so remember that those are two different things, two different steps. Sometimes you don't even have to do the second step, but the first step is you have to deal with the fact that the coordinate system at every instant is rotating, okay? You got to deal with those I dot, J dot, K dot terms. That does not deal with the fact that the coordinate system is in a different orientation at every instant. That only deals with kind of its angular velocity at every instant. So then if you want to convert it to a single non-moving coordinate system, you have to deal with the fact that the orientations are different. Anybody have any questions to help clarify that? Or maybe that makes sense, that would be great, but I know this stuff is a little tricky, you know, a little subtle. What? Oh. That came from the fact that, so theta, we're doing it at time equals 0, right? And so if you look at the function for theta, cosine of 5t, so you get 1 for theta. Yeah, and so theta always tells you the orientation of the r axis. Yeah. Any other questions? Okay, so now we're getting into really the main thing that we're going to use these rotating coordinate system equations for. And that is, I'm going to call it superimposed motions. The example that I'm going to use is we have two bodies. Okay. And this body, I forget the name of this thing, but this guy is spinning this way. Okay. And then the wheel is spinning this way. The red one is at 20 radians per second. And the disk is, so for a camera that's fixed on that 20 radians per second rotating thing, this disk is just spinning at 5 radians per second. And of course, those two things together lead to a really complicated motion. Okay? And we want to calculate, let's say, the acceleration of this point P. Okay? Now, we've done superimposed motions before. So what's the difference between this setup and, let's say, you know, this is doing something, this is doing something. So first of all, what's the fundamental difference between these two systems? Because this second one that I've drawn down here with the two arms, we already knew how to calculate that. That was one of the earliest topics that we dealt with, calculating the acceleration of that point P. But up till now, we don't know how to do something like the thing above. Can you put into words what the difference is there? Yeah.
All the objects have two different axes of rotation.
Yes. And it's not just that they have two different axes of rotation. I mean, you're on the heart of it. The really key thing, I was about to get up and point at stuff, but then this is the key thing. I need this on video. I should carry my computer up there. The key thing is there's always a horse and a cowboy. Okay? One motion is riding the other one. That's just a fundamental fact. In this example, the simpler example that we already know how to do, no matter what the horse does, the axis of rotation of the cowboy is the same. Okay? So if the cowboy's orientation doesn't determine, no, I gotta be careful here. If the horse's orientation doesn't determine the axis of rotation of the cowboy, it's easy. Okay, so this lower example with the arms, no matter where this goes, like if it's up here, the axis of rotation of this one is still into and out of the page. If this is down here, the axis of rotation of this is still into and out of the page. Are you with me on that? If, on the other hand, the horse's orientation does determine the cowboy's axis of rotation, that's when we have to use rotating coordinate systems. So use a rotating coordinate system, and we're going to use a rotating coordinate system that's fixed to the horse. Okay. It kind of makes sense that you would use a coordinate system that's fixed to the horse because we have two simple motions. If you combine them, it's a complicated motion, but if you sort of put your coordinate system in the middle of the two motions, both of the two are kind of simple in that coordinate system. So that's what we want, okay? So let's think about let's think about this case, okay? If this is in the position that's drawn there, okay? What's the axis of rotation of this disc? It's into or out of the page, right? If this is rotated down 90 degrees, this disc, we're looking at the flat part of the disc, and the axis of rotation is up or down, okay? So that's a case where the orientation of there's something that's being ridden and something that's riding it, okay? If the thing that's being ridden determines the axis of rotation, then you're going to fix your coordinate system to the thing that's being ridden. Okay, it doesn't work the other way, notice. No matter where this disc is in its rotation, doesn't have any effect on the axis of rotation of the horse. So they're fundamentally different that way. Okay, it's still, this thing is still rotating about an axis that way. So the first step is you need to identify the difference between those two things. Okay, so let's see how this works. So we're going to use a coordinate system that is, okay, so the horse in this case is the body with the rotation drawn in red. The cowboy is the body with the rotation drawn in green, right? Green. And so So I'm going to put my coordinate system here. With the z-axis coming out towards us. And this coordinate system is fixed to body 1. Okay. And notice that the idea of this now is, well, if we have that coordinate system fixed on body 1, now the axis of rotation, no matter what the orientation of body 1 is, the axis of rotation is z, the way I have it drawn. Okay? Because, as this thing turns, so now say this thing is rotated down 90 degrees. I mean, the axis of rotation did change, but the z-axis also changed, and so it's still rotating about z. That's the idea. Okay, so so this is the horse. Okay, so let's start filling this out now. We're going to calculate, so if this is p, the acceleration of p is equal to, that coordinate system is rotating, so it's going to be equal to the acceleration of p observed in the coordinate system plus omega dot cross position vector plus 2 times omega crossed with the velocity vector of p that's observed plus omega cross quantity omega cross p. And now I think the easiest way to keep things straight is to just start writing down these individual values. Once you have all of those, then you just plug it into your calculator. So let's start describing some of this stuff. Omega, what's that? Let's start with that. What's our omega? That's maybe the easiest one.
Angular velocity.
That's the angular velocity of the coordinate system. So that's going to be the angular velocity of the horse compared to like a fixed coordinate system. So looking at this, what value is that? 20, yep. And it's about the x-axis. So this is going to be 20, 0, 0. Okay. We also need omega dot. Is that changing? I didn't say anything about that, so no, we're assuming that's constant. So this is 0. Okay, now we need the position vector, the velocity vector observed, and the acceleration observed. Okay, the position vector, so the position vector is just going to be in this coordinate system, what are the coordinates to that point P? Oh, I didn't give a radius. I need to give a radius.
It should just be 0, negative r is 0.
Yeah, let me give a radius. I meant to. So let's say this radius is 0.4 meters. So position is just going to be 0, negative 0.40. And now the observed velocity and observed acceleration take a little bit of thinking at first. But the reason that we put the coordinate system fixed to the horse is because it changes because now the motion of this thing to the coordinate system looks like a simple motion. This is just in circular motion now, okay? So all we're gonna do for the observed velocity and observed acceleration are circular motion calculations, okay? It's like, you can imagine that this isn't going anywhere, because to the coordinate system, it's not, you know? So the observed velocity of P is omega cross R, okay? Remember, R and P are not the same thing, so I think it's a good habit to always remind yourself when you see rho, R, P, remind yourself of the definition of those things so you don't get confused, you know? What's omega? There's two omegas, but this is the little omega. Yep.
5 radians per second.
Yep, exactly. In the negative z direction. Anybody have any questions about that? And R is equal to, so the definition of R is from the center of the circular motion to the object. So in this case, that's the same as the position vector, but that's not always the case. And so the velocity of P observed by the coordinate system is -2, 0, 0. And now we'll do the same thing with the observed acceleration. What do we use to calculate the observed acceleration? Yep, exactly. Yep, because it's just circular motion. So alpha cross R plus omega cross quantity omega cross R. We already know omega and R. We just need alpha. What's alpha for this example? 0, because we're assuming that's a constant angular velocity. So this is equal to 0. And so plug those all in. And you get 0, 10, 0. I mean, essentially, since there's no angular acceleration of this body, if you assume that the horse is fixed, there's no angular acceleration of this body, so the only acceleration is centripetal, and it's going to be equal to 5 squared times r, toward the center, and that's what we got. Now you just put it into this equation. We derived this equation last time. Now it's just a formula like any other formula. So the acceleration of P is equal to 0, 10, 0. Plus capital omega dot cross P, that's 0 because omega dot is 0. Plus 2 times, so 2 times capital omega crossed with the observed velocity Who can do that in their head? Yeah, very good. Anytime vectors are parallel, their cross product is 0. And then plus omega cross quantity omega cross P, and our position vector is 0, negative 0.40. Do these calculations, and in this case, because of the way things are aligned, this looks simple. We just get 0, 170, 0. You won't always just get a single non-zero component. But without this rotating coordinate system approach, we'd have no way to deal with this. Okay? Any questions about that? Yeah.
I'm just doing mental math.
Yeah.
So I'm a bit confused. So it's 20 times 0.4 or negative 0.4, which would be -8, correct? And then that times 20.
Oh yeah, but then we add the 10 to it.
Oh, add the 10.
Yeah, you're right.
I was getting confused.
I never like it when people start digging into the details, but in this case, that's right. Any other questions? Let's do another one quick. That one I was real chatty. Let's just go through one sort of like more straightforward, straight through. Okay, so let's say that, so there's a wall, and the hinge attached to the wall has a body like that, and then there's a second body rotating this way. Let me make that a little longer to try to this one is rotating about that axis this way, like in the, let me draw a coordinate system. So here's the coordinate system we're going to use with the z-axis out of the page. So that red rotation is in the positive x direction, and that has a magnitude of 10 radians per second. And this body is rotating this way at 5 radians per second. And we'll assume those are both constant angular velocities. And then this distance is 0.2 meters, and this distance is 0.2 meters. And we want to calculate the acceleration of this point P. Okay, of these two bodies, which one is the horse? Yep.
The one attached
To the wall, that's right. And so now you have to ask yourself, does the orientation of the horse affect the axis of rotation of the cowboy? Yes. So the orientation of the horse, that's this one, affects the axis of rotation of the cowboy. So we're going to use a rotating coordinate system. And this rotating coordinate system is going to be fixed to the horse. Okay. Now, a coordinate system can be non-inertial in two ways. If it's rotating, which is what we're dealing with. Also, if the origin is accelerating. So there's a million places, infinite places, that you can fix the origin of the coordinate system to the horse, right? But there's only one where the acceleration of the origin is 0. And that's at the wall, okay? You can do problems like this with the origin, say, here, but then you'd also have to use relative motion to account for the fact that the origin is accelerating. Okay? And I'll do some problems like that as we start getting used to it. But for now, you just always want that coordinate system. If you want to make it as easy on yourself as possible, you want that origin to be fixed. Just the axis rotating. So you want the origin not accelerating. Okay, well, now we know we're going to use that the acceleration of p is equal to the acceleration of p that's observed by the coordinate system plus capital omega cross p plus 2 times capital omega cross velocity of p observed by the coordinate system plus capital omega cross quantity capital omega cross p.
Isn't it omega dot across p for the first term? Or the
Yes, it is. Thank you. Thank you. Okay, and let's start filling this stuff out. Capital omega that's 5 in the positive z direction. Capital omega dot is 0. The position of p, the origin is all the way over at the right, so this position is going to be negative 0.2, negative 0.2. You with me so far? Now the observed velocity is lowercase omega cross r. Lowercase omega is 10 radians per second in the positive x. Here we have a case where r is not the same thing as position because r is the vector from the center of the circular motion to the point. So what's that in this case? Yep.
0, negative 0, 2.
Yep, that's right. It's just the vector pointing from here down to p. So that's 0, negative 0.2, 0. And so this observed velocity is 0, 0, negative 2. How do we calculate the observed acceleration? It's just circular motion, so this is watermelon. Our alpha is 0 again. And so this comes out to be 0, 20, 0, using the r and the lowercase omega from the velocity one. And so now we can put it all together. The acceleration of that point P is 0, 20, 0 plus omega dot, capital Omega dot cross P, which is 0 because omega dot is 0, plus 2 times 0, 0, 5 cross 0, 0, negative 2. Who can do that in their head? Yep. That's not always going to be 0, but the last two examples it has been. Plus 0, 0, 5 cross quantity 0, 0, 5 cross position do all these, add them up, and you get 5, 25, 0. Okay. Any questions about that? Yep.
So if we have two rotating objects that are fixed together in different, with different axes of rotation, is it always going to be one is changing the axis of the other?
Yes,
Or okay. So
that's right. That's another way to say it. You're right.
Yeah.
Exactly. So I'm going to give you some of these to work on. Try to do them. If you can't, that's all right. I'd be happy to do as many as you want on Monday. But if you try to do them, then when I do it, if you get through them, great. If you don't, at least then when I'm going through them, you can see where you got confused when you compare my answers to where you got stuck. You know what I mean? So, okay, that's it.